Our topic for this week is polynomial functions. I'm going to save the sort of scary, mathy, like formal definition, but polynomial functions are functions built up by a finite number, so there can't be infinitely many of them, but many, that's the poly is the root word there. So many terms where individual terms look like a variable raised to some power. We write it as n, possibly with some real number coefficient. So this is just some number. This exponent has to be a positive integer, meaning it's a positive whole number, like a counting number. And then for a polynomial, you can have a bunch of these that are added, subtracted, or possibly multiplied together. So what that means is that, let me just make quick notes. Well, you know what? We've already kind of made notes. Again, the powers have to be positive integers, real number coefficients, and you can have as many of these terms as you want as long as they are, as there are finitely many of them. So some examples of polynomials would include things like stuff that we already know, like y equals x plus 3. That's a linear polynomial. Quadratics, which we've just been studying for the past week, like x squared plus 2x plus 1. That's quadratic. Here's another example. Let's say 17x to the 5th minus 3x cubed plus x squared minus x. That's a polynomial. Don't worry about the naming part, but the conditions that we want to check is that each term has a real number as its coefficient, so we're not going to see I show up as a coefficient, and the exponent has to be, again, some positive integer, so a positive whole number. So here are some not examples. One over x, that's a function, but it's not a polynomial function. X to the 1/2, that's not a polynomial because that power is not a positive integer. We'll get more into this later in the semester, but that's the same thing as the square root. So our variable is not going to show up in the denominator. It's not going to show up inside any kind of a root. Or combinations of those things. So that's not a polynomial either because this power is a negative number. This power is a fraction, and we're looking for positive whole numbers. Okay, now for a polynomial function, there are some terms that we need to be familiar with. So here's, again, just one more example. And it's going to turn out, and we'll see why in class over the first couple of days of this material, that by looking at this, we learn a lot of things. Now, we've kind of already seen this a little bit with the quadratic stuff. We've done a lot of talking about, for a quadratic, whether it opens up, whether it opens up or opens down, which is based on whether the x squared term is positive or negative. Now, the thing that makes it quadratic is that that square term shows up. So in general, we call this the leading term. The leading term is the one that's in front if we write it in standard form, which is, again, like descending order of the powers. But that means the leading term is the one with the highest power. Whatever that highest power is, we call it the degree. So the highest power that appears in a given polynomial, that's its degree, in this case 3. This example, the degree is 3. Again, we'll get more into this in class. For now, we're just worrying about kind of the terminology, what everything means, so we can talk about it. But the degree is going to tell us a lot of stuff about how the function behaves and what it does. So that'll be one of the first things that we kind of look to identify is what that degree is. So the leading term here is negative 2x cubed for reasons that, again, will become clear, but we'll often talk about the leading coefficient as well. So that's just exactly what it sounds like. It's the coefficient on the leading term. So in this case, it's negative 2. Okay, so this is a polynomial with degree 3 and leading coefficient negative 2. Now, and again, we'll see more of this as we get into it, but what this means is that the degree 3, when we sort of go out far enough in the function, this term does most of the work in determining how it behaves. These lower order terms, when x is, I don't know, 1,000 or something, cubing is much, much bigger than squaring, right? Or any of the lower order stuff. So the further out we go, the less and less these kind of matter or contribute to determining the value of the function, and the more and more it starts to look more like, just whatever this is. That's why it's important. Again, we'll see how that kind of plays out as we get into this stuff in class. Let's do one more example real quick. Let's call it g of x is negative x to the 4th plus 3x squared minus x plus 3. The degree there would be, and let's be a good place to pause it for a second. Degree would be 4, and the leading coefficient, negative 1. This whole thing is the leading term. And then again, we're sort of, decomposing or breaking that down a little bit. The degree is the power itself, so 4, and then the leading coefficient is just whatever the coefficient was. Okay, so again, terminology stuff, the leading term, the degree, and specifically the coefficient on the leading term will be important. Okay, the other sort of definition stuff that we need is some terminology related to the graphs. So polynomial graphs are going to, look, this is an example of one. They're going to vary more than quadratics. Quadratics, we're always talking about a parabola. It could open up or it could open down. It could be, sort of skinny or wider. But apart from that, they'll have the same basic shape. That's not true anymore with polynomials. They start to vary more and more. But the thing that is consistent is that they're always smooth, continuous curves. Kind of like an old wooden roller coaster. So none of the, no loops or anything like that, but the kind of thing that, you could sort of smoothly travel along without being, thrown off or anything like that. So they go up, they go down, whatever, but it all happens kind of gradually, right? So none of like this kind of stuff can happen. So it's always kind of a smooth curve. If you sort of zoomed in close enough here, it would almost look straight. That's the idea. Terminology stuff that we need. Turning points. X-intercepts, which are also sometimes called zeros or roots. I probably won't call them roots very often, but I may kind of use these interchangeably, x-intercepts and zeros. X-intercepts means where you cross the x-axis. Those are called zeros because at the x-axis, points are going to look like that, right? So that's why they're also called zeros. And then describing the end behavior. Okay, so what these terms mean, turning points are places where the graph changes direction. So if we are, again, thinking about this like a roller coaster track, he's smiling, you can't tell. And we're moving along this track from forever until we get to here-ish, we're headed up, right? We're like moving uphill the whole time. But then there's this point where, you know, the thing pauses for a second and like your stomach drops, and then we drop off and we're headed down for a while until we get here. We get to the bottom of this little hill and then we're going up again. So this thing is initially increasing, moving up, then decreasing as it moves down, and then increasing again. And assuming that we see everything there is to see about this graph, like that's it. These points are the turning points. So this function has two of them. And again, they're right here and right here. It's these points where the thing changes direction. So those are going to be the like the top of a hill, if you want, like this first one that we see, or the bottom of a like valley, right? So those are turning points. X-intercepts means the same thing it always has, right? It's points where you cross the x-axis. If we're talking specifically about how many of them occur and rather than where they are, we'll get into finding where they are later in the week with solving equations and stuff. But for now, just how many of them there are. There's one, it's right here. So that's an x-intercept. This is a turning point. And so is this. Okay, and then the end behavior, we're basically talking about, you know, if we kind of ignore all of this, right? So polynomials are always going to have this sort of wiggly stuff going on in the middle. But if we ignore all that and just look at it big picture, like if I took this graph, and this is just a picture of it, so I can't do it here, but if I just took this graph and zoomed way out, what would I see? What I would see is that this end is pointing down in the direction of negative infinity, and that on the other side, this end is pointing up. So again, talking about sort of the big picture, what this graph tends to do everywhere except for this little box of stuff in the middle that I'm not looking at, but basically this function is increasing everywhere, right? As I read left to right, we're sort of moving up over almost the whole domain of the function, again, except for this box that I've, you know, kind of covered up for now. To describe that, we can say that a couple of ways. It gets kind of clunky a little bit. You can sort of picture yourself like standing in the middle, and some books or sources will say like, well, if I look to the left, then the graph is sort of falling away from me. And if I look to the right, then the graph is rising away from me. So, you know, it falls to the left and it rises to the right or something like that. What I usually do is just, you know, I'm not standing in front of you right now, so I can't hold my arms up in the air. But as you can probably imagine by this point, what I tend to do is hold my hands up in the air to, you know, show which way the thing is going. So what I usually do is just draw arrows. So that end's pointing down. This end's pointing up. So I would describe the end behavior of this thing like that. That, you know, there's this middle section where it gets kind of wiggly and does some stuff, but the ends look like that. If I ignore the middle part, then the left-hand side is sort of pointing down, the right-hand side is pointing up. Okay, and then the other definition there on the notes, multiplicity, we'll talk about that later on because it kind of builds on some other stuff first. So that should give us a start for the stuff we're going to look at in class. Thank you, and I will see you then.